Okay, now I'm going to talk about the redshift of light from the star S0-2, which is revolving around the center of our galaxy in general theory of relativity and in our theory, Yarman-Kholmetskii gravitation theory. Okay, now let's have some characteristics of the star S0-2, which orbits around the center of our galaxy. You see it over here as the green orbit, which is the closest to the center of the galaxy. Now, here are a few properties. The mass of the black hole of our galactic center is called the Sagittarius A star, which consists of 4.3 million solar masses. The mass of S0-2 is 14 solar masses. The period of the given star is 16 years. I like to recall that the period of Jupiter around the Sun is only 12 years. The period of Uranus around the Sun, on the other hand, is 84 years. And the major axis of the given star S0-2 is about 970 astronomic units. The gravitational potential parameter alpha is about 3.3 times 10 to the minus 4. The pericenter distance, which is the closest approach of the given star to the center of the galaxy, is 120 astronomic units. And the speed of the given star at periastron is about 6,000 kilometers per second. It's huge. It may be even greater than this. So the distance to Earth of the galactic center is more than 25,000 light years. Okay, now I like to state the short story behind the given work. My friend, dear Professor Metin Arık, attracted our attention to the article which was published in European Space Agency. Hubble discovers mysterious black hole disk, which appeared in 11th of July 2019. So the article said that astronomers using the NASA Hubble Space Telescope had observed an unexpected thin disk of material encircling a supermassive black hole at the heart of the spiral galaxy, which is called NGC 3147, which is located 130 million light years away. This was very interesting. So something unexpectedly close to the center of a black hole was observed. So we swiftly made stationary orbit and light redshift calculations near a black hole in both GTR and YEFAK that led to discovery of a softened or less pronounced redshift near a black hole under YEFAK as compared to what is predicted by the general theory of relativity. Okay, now here is an intercept of our calculations. It is unity normalized. We predict the YEFAK redshift as compared to what GTR predicts. So this was done at around mid-July. And we have uploaded our file in academia. So we see over here as the green line, the GTR prediction, as far as the redshift, unity normalized redshift is concerned, thusly predicted by the general theory of relativity. And the upper YEFAK colored curve is the prediction we have made ourselves about the redshift softening near a galactic center versus the alpha parameter. So at the same time, though, we asked ourselves, why don't astronomers look at our next door, which is the center of our galaxy, instead of surfing as far as 130 million light years away? Fortunately enough, right after we were wondering about that question, we got a paper which was published in August 16, 2019 from our friend Professor Recep Avcı of University of Montana. And you see over here in this slide the radial velocity of S0-2, which can be easily related to the redshift of light coming from that star versus the period of time of observation. So you see that the blue curve on this figure represents the GTR prediction, and you have data implemented all over. And what is observed is that the data clearly lie below the prediction, GTR prediction. So the reported deviation was about 12%. There's a maximum deviation at the periastron, the maximum you observe toward the right-hand side of the plot, and the deviation decreases as the star gets away from the center of the galaxy. Okay, so we were quite excited when we saw this, because that was exactly what we predicted, a softening. Of course, we had to check whether the softening of the redshift we had predicted can cover up satisfactorily the data as compared to what is predicted by the general theory of relativity. Okay, now let me explain a little bit what the radial velocity is about. So forget about the first term and the last term on the right-hand side of the first equation you see on the slide. So the PV sub z, okay, it's 0-2 line of sight velocity. So everything is adjusted to the sun, to our sun, which is, as a matter of fact, in motion around the center of the galaxy with a velocity of 300 kilometers per second. Never mind, as I said, never mind also about the last velocity. So there are two velocities, there are two parameters in this radial velocity expression. So the first one is v, or as a matter of fact, is v square. It is the orbital velocity of the star of concern. So the v squared divided by 2, which we should be interested in, it says the kinetic energy of the star around the galactic center at the given moment, and it is normalized to z. So that's how the radial velocity quantity is defined. So the whole thing is related to the redshift of light coming from the star of concern, as I said. So this points to the redshift component measured due to the motion of the star around the center of the galaxy in orbit. So it is over here clear that because of the translational motion the star undergoes in orbit, especially relativistically, the light frequency should be redshifted. Okay, so that's the first parameter which enters into the definition of the radial velocity. The second one consists in the strength of gravity. It is also normalized to see. It's made of alpha, the gravitational potential intensity that I had just talked about. And it is at times c. It's just a radial velocity component definition. The second component of the shift of light coming from S0-2 is made of, according to the general theory of relativity, the curvature is due to the curvature because of the increase of gravity intensity as the star dives into the vicinity of the galactic center. So it experiences more intense curvature. So then, according to the general theory of relativity, the frequency of light that comes from the star, just because of a given fact, should be redshifted. So these two components, classically speaking, general theory relativity-wise, makes up the radial velocity or the redshift of light coming from the given star. So this is only a Newtonian approximation, as you see. So the authors did not have to consider fancier calculations simply because the gravity intensity at the periastron, which is the maximum gravitational intensity the star experiences, is only around 3 times 3 10 to minus 4, which is about only 100 times greater than what it is on the surface of our sun. Okay, so then we have, as you see, the equation 3, the radial velocity definition, which is nothing else but the redshift exactly of light issued from the star. It's made of the two components I just mentioned. So it is due to, first of all, to the translational motion of the star on its itinerary and the intensity it experiences in orbit at the given time. Okay, now, observation of the difference of RV minus V sub z, which is the radial velocity which we are interested in, meaning the redshift, seem to only partially conform to general theory of relativity. All the same, over the entire data set, the difference RV minus V sub z, the radial velocity difference, or adjusted radial velocity, as calculated in general theory of relativity, is 12% greater than the corresponding statistical best fit to the measured data. So this leads to an alarming difference of about 15% between the periastral GTR velocity and the measured velocity of the star S0-2, which is totally inadmissible from the astronomical standpoint. Note that we are still in a regime where gravity is not very strong, which we underlined before. So it's only 3 point something 4 at the most, 10 to minus 4. It is so much so that the authors of the given source use the post-Newtonian approximation in the above equation. So that much violation in Keplerian orbit would point to a change in S0-2's orbital period amounting to 2.4 years. Can you imagine that? Out of 16 years, which is the period, the measured period, had the orbit been circular. This is just enormous. So you measure something, the same thing, in other words, based on the redshift of the light issued from the star, and you measure visually the orbit. So the orbit period, you come out with a difference of 15% in the Keplerian orbit. This is just enormous and inadmissible. So we firmly think the discrepancy is irremediable, and thence the general theory of relativity is over here badly falsified, I would say. Okay, now I'm going to summarize how we did our calculations based on YEFAK. And first of all, I have to summarize YEFAK theory at hand, our theory. It is interesting to state that YEFAK establishes its total energy equation for the given star straightforwardly and in just an integral form. This is just, I would say, miraculous. It is just based on the law of energy conservation, embodying the energy and mass equivalence of the special theory of relativity, and nothing else really. So the mass of the star, already at rest, if we could conceive, if taken to a gravity environment, would decrease due to the, as I say, mass and energy equivalence of the special theory of relativity by e to the minus alpha exponential minus alpha, which is the gravitational potential intensity at the given location. So then, if you take this decreaseless mass to the orbital motion the star undergoes, you have to multiply it by the Lorentz factor. So you have over there, as you see on the slide, the equation 5a, which states rigorously in YEFAK and straightforwardly, in only few lines, few steps, the total energy of the star in motion in gravity. So this is already one thing. We have to remember that, though, over here, alpha includes the distance, as you will recall, the gravitational constant times the mass of the black hole situated at the center of the galaxy, divided by the distance of the star to the center of the galaxy times c squared. But that distance in YEFAK theory is not the distance measured by the distant observer, but it is the distance which is assessed by the local observer, which is supposed to be attached to the star. This is brought in simply because, as we see on the bottom of the page, the gravitational constant divided by the distance squared to the center of the galaxy as measured in orbit, as assessed by the distant observer, is strictly equal to the gravitational constant, but measured on the star, just Cavendish-wise, divided by the distance that observer, the square of the distance that observer measures as referred to the center of the galaxy. So this is what we call R sub 0. So in YEFAK theory, the gravitational constant is not really a universal constant, it's a proper constant. When proper, it's okay, the constant measured by Cavendish, it's nothing else. But this, it doesn't depend on the local observer, it doesn't depend wherever it is measured. But what the distant observer measures as referred to S0-2 star is something else. In any case, the last equality you see on the bottom of the page persists. So we have the nice relationship between the two distances of concern. Quantum mechanics came in. So suppose you have a hydrogen atom on the surface of the star of concern. So according to the present approach, the size of this hydrogen atom will be enlarged by e to the alpha as referred to the distant observer. So all distances, as a matter of fact, will be altered that way. Not only that of hydrogen size. So the hydrogen size is just a stick meter, nothing else. So the distance measured by the distant observer of the star to the center of the galaxy is R, and it's equal to the distance measured by the local observer attached to the star, R sub 0, times e to the alpha. And in alpha comes into question not R, but R sub 0, as I said. Okay, indeed, when we come to dig in our quantum mechanical relationships, we can remark that due to our general quantum mechanical relationships between the quantities mass, energy, frequency, time, and size, the variation of the rest mass of the test particle, say hydrogen atom for instance, by the static binding energy, affects the internal time rate of the particle and dictates a corresponding transformation of spatial intervals in the presence of gravity. Like in GTI, gravity does in effect alter, albeit post hoc, metric of space-time in YEFAK theory too. However, to our best knowledge, the present theory is the only gravitational theory that brings in quantum mechanics in such a great symbiosis with the rest of the theory, which makes that we can use the same approach not only for gravity but for instance for a bound muon. So a bound muon means a muon bound to a nucleus. So the bound muon will get retarded just like the shift we have expressed for the star S0-2. So the muon, when bound to an atomic nucleus, its decay rate will get decreased due to its motion around the nucleus, also to the decrease of its rest mass because of the binding it delineates to the nucleus already at rest. Okay, now let's step to the similar total energy expression, but for GTR, general theory of relativity. So we can get a similar equation to the total energy expression of the present theory I have just presented in GTR as well. This is not everywhere, really. The first place we could locate it was the equation 88.9 in the book of Landau and Lifshitz. But this results from a long, cumbersome derivation. I'm not going to go into the details of these derivations. Anyone who knows GTR knows about these derivations. So comparing now the YEFAK theory's overall energy equation, which was the equation 5, above, in the radial symmetry case, with the known expression of GTR for the energy of the test particle in the Schwarzschild metric, we have equation 6. So this equation says that the total energy, mc squared, is the total energy in free space of the given particle, which is in this case the star is 0,2. So if it were in empty space, its total energy would be mc squared. So its total energy is decreased by square root of 1 minus 2 alpha, which is due to curvature in GTR. And times gamma sub 0, just like we had gamma coefficient, the Lorentz coefficient, in the previous case. We also have over here the coefficient gamma sub 0, but here 0 means that the velocity of concern, the velocity of the star, is measured by a local fixed observer, which is fixed in orbit. So it's not measured by the distant observer, but that fixed observer. So when the star crosses that fixed observer in orbit, so the fixed observer measures the velocity of the star, out of which he could determine the Lorentz coefficient. So as we miraculously, I would say, see, the two expressions in both theories come to be the same up to a third order tighter expansion. And we can recall that for the beginners, I would say, the coefficient 1 minus 2 alpha, which appears in equation 6, is nothing else but the component of the metric tensor for a test particle in the gravitational field in the limiting case in the general theory of relativity, which points to nothing else but to the curvature. Okay, so the GTR and YEFAK theory thusly converge in the limit of a weak gravitational field. So we have the same equations. In the weak gravitational field, we have the same redshift. We have the same motion. I'm not going to enter into the details, but so both equations provide equally successful explanations of gravitational redshift, gravitational bending of light, Shapiro delay, and precession of perihelion of planets in all cases where thusly the gravitational field remains, as I said, weak. One should moreover mention that the YEFAK theory also achieved considerable successes in the explanation of modern observations where the limit of weak gravity is abandoned. A derivation, say, of the alternating sign of the accelerated expansion of the universe without the need to involve a notion of dark energy, presentation of the Hubble constant, which we can obtain analytically from the theory, and furthermore, the elimination of the information paradox of black holes of the YEFAK type, simply because we have no singularity in the present theory. So YEFAK's prediction of the extra shift between emission and absorption resonant lines in a rotating system also should be underlined. Indeed, besides the points I had just underlined, we wish to spotlight a recent experimental fact which we had predicted and unveiled, which is the extra energy shift between the emission and absorption resonant lines in a rotating system. So the references are given over here. That was successfully explained under the present theory, while still remaining as a puzzle for general theory of relativity, and Professor Kholmetskii has in effect just now delivered a speech on the entire story behind it. So let me now analyze the redshift of light from S0-2. So we are going to determine the redshift in both frames, I mean the GTR frame and YEFAK frame I have just summarized. In the analysis of the motion of the star S0-2 around the center of the galaxy, we can apply the approximation of the one-body problem where the energy of an orbiting star can be considered as a constant value and its vanishing differential directly yields the motional equation of the star, both in GTR and YEFAK. This is not a casual way of handling the equation of motion in GTR though, but anyway, since we have a total energy we had derived out of GTR, we can use it now via differentiating it to obtain an equation similar to the Newton equation of motion as well as to YEFAK equation of motion. Okay, in order to simplify the mathematical side of our analysis, but without any loss of generality, we will now calculate the radial velocity of the star S0-2, particularly at the periastron, and then compare the results of GTR and YEFAK calculations with the observation. So we will use in this approach the radius of curvature, which is equivalent to the circular motion. So at the periastron or anywhere in orbit, we can replace the general elliptic motion of S0-2 by a commensurate circular motion where, as is known, the effective acceleration of such motion can be linked with the actual acceleration of the star via the lengths of the major and minor axis of its elliptical motion. More specifically, the closest distance will be multiplied by the square of the semi-major axis divided by the semi-minor axis length. So with A being, as I said, the semi-major axis and B being the semi-minor axis in order to obtain the equivalent circular orbit radius. So over here, we first take the differential of the total energy expression we have pinned down with regards to GTR. The total energy must be conserved. We can indeed admit that the system made of the galaxy center, the Sagittarius, the black hole situated at the center of the galaxy, and S0-2 consists in a closed system, and the total energy of it should be constant. So differential of the total energy will be zero. Since the total energy of the black hole is the same, so we don't have to mind about it. So we mind about the total energy written for the star S0-2, then within the framework in GTR. So we differentiate it. So we have over here the equation 7, which may be not so usual even for experts in GTR, but it is there. It can be easily obtained. And so we have on the far left the Newtonian force, I would say, per unit mass. So in GTR it's decreased in this form by 1 minus 2 alpha times 1 minus v sub 0 squared divided by c squared, and for a circular orbit we have the v squared in GTR divided by the distance of the star to the center of the galaxy. So recall over here that the velocity of concern is measured by the local observer, and the distant observer would read equation 8 really. So v is the same velocity but measured by the distant observer. V sub 0 is, as I said, the velocity as measured by the observer attached to the star. So we can thusly write the velocity as observed by the distant observer and within the framework of the generator of relativity as equation 10 to a sufficient accuracy of calculations at alpha to the power of 3/2. So now we can from here on write down the redshift as normalized to unity in GTR. So it consists of the two components as I summarized just a few minutes ago. So it's made of the intensity the star experiences as well as the motion it undergoes. So the first term is due to curvature in GTR in general term of relativity, and second term is the special relativistic term. So this determines the equation 11 determines the overall redshift of light due to both the effect of motion of the star, that's the second order Doppler shift, and the effect of gravity in a radial symmetric gravitational field as per general theory of relativity. So this allows us to write the equation 7, which is over here. So this looks like a Newtonian equation, but the Newton force intensity per unit mass is decreased by the two coefficients over here. Anyway, okay, so we land at equation 12 for the radial velocity in GTR in terms of the velocity of the star in orbit as observed or measured by the distant observer. So this can further be written as equation 13, which can be straightforwardly generalized to an elliptical motion. Okay, so now to calculate the acceleration of S0-2 in orbit, we will use equation 14 over here, which would be v squared divided by r if it were always circular. But this is an elliptical acceleration really at the given location, which is the periastron. At the periastron, it should be written as given in equation 14. So v squared times b divided by a squared. So we can really imagine a squared divided by b. We can say this anyway. So this is the corrected equivalent circular motion's acceleration, but written for the given location in elliptic orbit. Based on this equation, we can right away write this equation 15, between the velocity in orbit of the star and the redshift measured within the framework of the general theory of relativity is normalized to unity. Okay, there is a little something over here, but I'm not going to insist in it. We have also just a little correction to the intensity of gravity, but I'm not going to insist in it over here. Okay, now next we do the same calculations for the present theory. The present theory's total energy of the star is equation 5a. So this is it. That's the total energy. it looks very much like the previous total energy formulated by GTR. So since it should also be a constant in a closed system, so for the given system, for the star, so mc square is the total energy of the star, or total rest mass, rest energy, I would say, of the star at infinity. So we differentiate the whole thing over here, which is a constant, so it will lead to 0 on the whole, and then we can write this equation for a circular motion in the arc case. So it's not identical to the previous equation, but it looks very much like the other one. Both of the equations in the weak field converge as expected to the Newtonian equation of motion indeed. So we have over here alpha sub 0, and we have alpha, as I mentioned a couple of minutes ago. So the first one is associated with the distance of the star as assessed by the local observer attached to the star, and alpha embodies the distance of the star to the center of the galaxy, but as measured by the distant observer. So using this relationship 17 over here, which is just a quantum mechanical gift to the present theory, or a gift presented by the present theory to the scientific community. So using it, we land at equation 18 over here, and therefore to the velocity expression of YEFAK is assessed by the distant observer to the accuracy of calculation at alpha to the power of 3 over 2. Okay, by analogy to the general theory of relativity analysis performed a minute ago, we can define the redshift still normalized to unity, redshift of light in YEFAK theory as given in this equation 20, which yields a relationship between the redshift and the velocity of the star as assessed by the distant observer in the present theory. So we like to write the equation of motion in YEFAK theory just the way we have done in the general theory of relativity, while bringing in the calculations the equivalent curvature. So we express everything as if it were a circular motion, but we of course take into account the fact that we deal with not a circular motion but an elliptic motion. So this is why we have over here square root of b divided by a. Again, I'm not going to insist in a little something detail over here. A little correction should also be brought to alpha. The alpha which was brought in by the quantum mechanical relationship before, and the alpha 0 chiefly are not the same, but I'm not going to insist in it as I said. Okay. So the comparison now of the overall redshifts predicted by the general theory of relativity and YEFAK theory of gravity. The foregoing equations, which we called 15 and 22, allowed us to express the difference. We are the corresponding difference of the orbital velocities of the star derived in YEFAK theory and the GTR correspondingly. That is this equation. So we just took the differences of the velocities and we expressed the difference of velocities in terms of the redshifts normalized to unity. Now we have to go one more step beyond, and we will have to express the redshift in terms of the radial velocity, so that we will have a relationship between difference of the velocities and the difference between the radial velocities as predicted by YEFAK theory and by the general theory of relativity. Both referred to radial velocity, which would have been furnished by Newtonian approach, which is, as a matter of fact, 0. Okay, so what we have over here, as I said, finally, an expression between the radial velocity expressed by YEFAK and radial velocity expressed by GTR. So what we observe is that there is a difference between them, which is expressed by the last term over here of equation 27. So that's our analysis indicates that at the periastron, S0-2's radial velocity as estimated in YEFAK theory turns out to be smaller than its radial velocity as estimated in GTR by the value of square root of BR divided by 2a times C alpha, which at the numerical values of concern brings a difference of 35 kilometers per second. This is something measurable. As a matter of fact, if we brought in the little correction I have just talked about, this would turn out to be even smaller, about 28, something like this, which would coincide exactly with data at the periastron, I would say. Okay. Now, we show this value as it is over here with a yellow dot. One can see that it agrees strikingly well. As I said, it agrees even better with it because it would go a little bit up over here. So 7 kilometers more. I have to skip this detail. I cannot insist because of the limitation of time. So we foresee perfectly, I would say, the divergence between data and general theory of relativity. So you see, this is the estimation, the best fit curve over here. So we are right on it via YEFAK really. So we have carried out the calculations for not only the periastron, furthermore for other points, for the midway, for instance. Okay, but anyway, the radius of the curvature is this. So the correction term between YARC and GTR becomes this. So it's square root of r divided by capital R, the radius of curvature. That's the distance of the star to the center of the galaxy divided by 2 times c times alpha, which is the intensity of the gravitational potential per unit mass per c square. Okay, then we have this ellipse equation, and we have this equivalent circular motion at the periastron, which coincide exactly at the periastron with the elliptic orbit. Okay, so in any case, the radius of curvature varies between a squared divided by b and b squared divided by a, midway between the periastron and apastron. In the apastron, it becomes again a squared divided by b. I'm not going to insist on the details. So we did calculations over here for the apastron. So we obtained something practically the same as what is furnished by GTR with the precision of measurements. So we have derived also at midway the result. The midway, I mean between periastron and apastron. So it becomes this 13.6. But if we take into consideration that little something, which I did not go into the details of, then this would become even smaller. Anyway, it still coincides, I would say, almost perfectly with the data. Then let's conclude. So in the present contribution, we reported how Young gravitational theory predicts a softened redshift of the light coming from the star S0-2 to Earth in comparison to what was estimated using the general theory of relativity. The difference between the general theory of relativity and Young predictions becomes insignificant in weak gravitational fields, where both theories converge to the same results. Thus, the closest approach of the star S0-2 to the center of the galaxy opens a unique window to test gravitational theories beyond the limit of a weak field. This is undoubtedly a valuable feature of the reported observations of S0-2, which allows us to qualitatively carry out a new test of the available theories of gravity, and where, in fact, general theory of relativity does not successfully pass the test. Namely, in contrast to the claim of the authors, which reported data that the relative deviation of about 12% between the observed radial velocity and the radial velocity calculated in the post-Newtonian approximation is insignificant. We have shown that this deviation implies a strong violation of the Keplerian law of motion of the star S0-2, which obviously is inadmissible from the astronomical point of view. We therefore came to have aspired to check out the Young's theory's description of the motion of the star S0-2, where, for simplicity, in our analysis, we carried out calculations of the radial velocities of S0-2 at the periastron and apastron, and in the midway as well. We can do it anywhere, really. The application of the present model to other locations is indeed straightforward, where orbital location data with respect time known beforehand, and we can calculate them. So I would conclude